This is basically an example line. This is a very simple, it looks actually very simple and straightforward line once you look at it running, but there's a lot of synchronization that has to happen. There's a lot of automation that has to occur on these pieces of equipment as the parts are flowing through. So those sequences will have to be tied in. And it looks like a fully optimized line because it is, and it's been optimized on a virtual twin, on a data-driven twin, basically before anything was actually designed or put on the floor. When this started out, it was nothing was working. There was a lot of buffers. There was a lot of things that are actually waiting on those conveyors for anything to happen. So the throughput suffered. There was a lot of rejects, and as soon as the data-driven twin was actually put in place, all these things got cleaned up, and all that happened before anything was built in the real life environment. So once you're done with that, you can take that and plug it into the full representation. Now you can see, if I take that operation that I optimized and I put it in my full plant, how is this going to work? Is it going to be too fast for anything downstream from it? Or is it going to have enough products coming into the operation from an upstream? And did I optimize it to the point where I moved the bottleneck to another department that now has to be optimized? So that's really the advantages of taking that twin and putting it into the global representation of the plant, to say, what kind of impact that's going to have on my operation? How is it going to affect the packaging? How is it going to affect my warehouse? Or how is it going to affect all the sub-assemblies that have to go into my operation? And you can do all that stuff live on the simulator. You can change whatever you need to do. You do the analysis, and guess what? If that proves to be a problem, you go back and readjust the main line and fix it up. But these are kind of the advantages of these type of systems.